Fine. You see, we have talked about till now what have we done. Basically, you can see that in the night sky there are so many stars, and so what we did is we first did a grouping. Okay, and these are the number of stars, and this is brightness, how bright the stars are, and we use the apparent magnitude, which depends on apparent brightness. So we use this. This was the first grouping of stars, or first characterization of stars. The next what we did after this was, we again number of stars over here now, but remember this is basically a 1D plot. This is not important how many stars are there. বুঝতে পারছো? What is important is that we do this sort of classification. So in a way these are both 1D classifications. Now this time what we are doing is we are saying that let us put all the stars at a distance of 10 parsec from us. Okay, so this is the distance. Then if we do so, then whatever apparent brightness they will have, this will correspond to absolute magnitude. So this is absolute magnitude, and this is the second grouping of stars. So this is what we have done. We have first done this first grouping, next we did the second grouping. Okay, so let us now proceed forward. What else can we do? Of course, before that, what we have to see is what are the various possibilities of observation. What do we expect to see? We have to first think of it. Remember, we are physicists, so even before expecting to observe something, we have to think that what should we expect to observe. Now suppose there is some sort of atom. Some atoms are there. Okay. Now when I say some atoms are there, so let us consider one atom. Then it has an excited states. Okay. Now if there is a, say, excitation, say from the ground state of this atom, what will happen? What will happen? You tell me. বলো, কে বলবে? হ্যাঁ, so it is in an excited state, right? After that it will come down to the ground state. Now you see there are how many possibilities of coming to the ground state? One possibility is straightforward, this one, right? But then again there is another possibility as well, this one. Of course, whether it will de-excite after some time through this path or through this path, this will depend on the properties of this level, right? We have learned this in nuclear physics, but I am not talking about the property at the time being. What I am saying is that it is possible that even after excitation to one level, we can see, so after excitation we can see multiple, this is the thing I wanted to discuss, multiple de-excitation lines. Okay, তাহলে বেসিক্যালি কি হবে? So we will basically, if this is a spectroscope, you can see, so there will be basically in this case 3 bright lines. You will see in dark background. Okay, so we will observe bright emission lines, not just one line. Here we are observing 3 lines in a dark background. Fine. So, and how does this look like in the spectrum? So if this is the spectrum, say, so we will observe something like this. I'm just giving some point will be there. I'm just giving you a rough idea. So basically we are talking about bright emission line just as a result of de-excitation. Okay, from this level and this level. So this is, you see, case 1, first case, a very basic case. Now let me talk about a different scenario. Okay, suppose we have a very bright source. Okay, and light from this source is being emitted everywhere. Okay, fine. Now suppose it is getting in a place. কি হতে পারে? Yes. Right now, you see, we have just discussed about, what did we discuss about? We discussed about the fact that after excitation, we can observe, it is possible to observe multiple de-excitation lines. Okay, we just observe this, talk about this discussion. Now, what I want to say is that next scenario, suppose we have a bright source, okay, fine, and there is an atom over here, and I tell you that from this bright source we will have all types of radiation coming, but the atom here, it also has its own energy levels, right? Suppose one of these photons correspond to this transition. So what will happen? What will happen is that এইখান থেকে yes, suppose যতগুলো photon এখান থেকে আসছে, out of all of them, the photon corresponding to this transition, it will be absorbed. Okay, and we will see this part, we will see all the other photons except this photon. So what will we observe? We will observe something like this. যদি এই দিকে আমার এই যে এইখান থেকে যেটা বেরোচ্ছে here, if the spectrum is something like this, then here the spectrum will be something like this. And what is this? There is no problem over here. Why? Because there was no absorption. But this thing corresponds to the absorption by this atom. This is the culprit which has called the absorption line. So this corresponds to absorption line. So if you see, this time you will observe a dark absorption line. Okay, now this is case 2. Are you able to understand? The atomer নিজস্ব energy level আছে, ঠিক আছে? Now if the difference of this energy level corresponds, this difference in energies from here to here, it corresponds to the photon, one of the photons over here, which has the same energy. Okay, then it will just absorb it. Is there any problem? This is how things work. Okay. Okay. So what is your question? Why called dark absorption line? Because this hot source, it is emitting all light in all wavelengths. Say, and here I am also observing everything, but except this particular frequency which is being absorbed by the atom. So if I observe in this part here, what I will observe, all the wavelength except the one which has been absorbed by this culprit atom. So what I am observing is something dark in the spectrum, which, so this tells me that there is someone out there who is eating away my stuff, or who is eating away the stuff given by this bright source, the photon. Some photons are missing, and this missing information is being told by this dark absorption line. Okay, you see, if we consider the light from this place, suppose the atom was here, but here there was no such atom, then we will observe a clear spectrum. So you can see all frequencies, all wavelength light is there, but there is no, in this case if you observe here, you will not observe any line, you will just observe bright colors. But here, because of the absorption of one particular frequency, you will observe one dark line, absorption line. Now suppose things get bad and there is yet another photon whose frequency matches this. If this is E0, if this is E1, and this is E2, and this is the E3. Now till now I have talked about this photon whose energy was equal to E1 minus E0, right? So this photon has caused this. Now suppose there was another photon whose energy was E2 minus E0. What will happen? Tell me.
আর একটা স্যার ডার্ক স্পট পাওয়া যাবে।
Yes.
যেটা ফ্রিকোয়েন্সি ওই E2 minus E0 এর সঙ্গে মিলবে যে ফোটনগুলো সেই।
Right. Now tell me which side it will be there.
ফ্রিকোয়েন্সি যেটা বেশি হবে সেইটা।
But here we have wavelength.
লেফটে হবে।
Very good.
ফ্রিকোয়েন্সি তো ওয়েভলেন্থ যেহেতু কম।
Right. Very good. So it will be like this. Okay?
ঠিক আছে।
ঠিক আছে? বোঝা গেল তো? So we will observe this time another dark line over here. So this corresponds to this one and this corresponds to this one. So this gives me information about E1 minus E0, and this gives me information about E2 minus E0. ঠিক আছে?
হ্যাঁ স্যার ঠিক আছে।
Okay, fine, good. Keep asking questions. Now, so let me do a overall. দেখা যাক তো কি হচ্ছে. Let us see. So, just a second. I have not saved it. এটা হচ্ছে না. Yes. Now, what is this? You can see. So, till now I have talked about 3 very interesting cases. Okay. Now let us now sum up together. So, you see, when this one is a source of light bulb, or say some source of continuous radiation. So, when we see this here, when we see some source of continuous radiation, then all the colors are present. Now this is of course observed through a spectroscope. You see, we see observed a continuous spectrum here. Now again, when this continuous spectrum is seen through a thinner gas cloud. Why thinner? If it is thick, then it will absorb very much. So I am saying thinner gas cloud. We will talk about it in terms of opacity later on. So what will happen when this continuous spectrum is seen through a thinner gas cloud? You see the clouds atoms here, you can see these spots, tiny spots, these are the clouds atoms. They will produce absorption lines. You see, continuous spectrum, and superimposed on them are dark absorption lines, the two effects we can observe over here. Now when this excited cloud is seen without a continuous source behind it and on a different direction, so there is no continuous source on its back, then what will we see? Then in this case, what we will observe are the emission lines, bright emission lines, which are emitted by the de-exciting atoms. So the atoms, they got excited after getting the light from this continuous source, and then during de-excitation in a different direction we will be able to see the bright emission lines. And as a result of this, now these two are quite complementary to each other. Now we can learn which type of atoms in this gas cloud are there from the pattern of absorption or emission lines. Okay, but there is a catch. Now can you tell me what the catch is?
Hello sir.
Yes.
স্যার বলছি যে যখন কন্টিনিউয়াস সোর্স ছাড়া আমরা ক্লাউড অফ গ্যাসটাকে দেখছি, যখন কন্টিনিউয়াস সোর্স নেই তখন স্যার অ্যাটমগুলো এক্সাইটেড স্টেটে যাওয়ার জন্য এনার্জি করা করে।
এই যে তো this spectrum, এই যে continuous source, it is emitting photons, right? And these photons slowly being absorbed by the atoms. How will it be absorbed? The photon which corresponds to some particular level of an atom will be absorbed by the atom, and the rest of the photons will just pass through it. And when we are observing the rest of the photons, we will get information about which photons have been lost. I mean, what are the energies of the photon which have been lost, and this is given in this spectrum over here. So we are observing continuous spectrum, and the dark lines correspond to the ones which have been absorbed. Okay, but there is a catch. Catch is, you might ask, sir, you see, if the atoms are absorbing and again after some time they are re-emitting the spectrum, then why are we still observing the continuous spectrum with dark lines? Why are there dark lines? Because we are already seeing the bright lines over here. If these bright lines do match with that of dark lines, then we should not observe the dark lines, right? The reason is that you have to remember that this emission is happening in all 4 pi directions, right? So the emitted photons are repeatedly absorbed. These, the ones which are being emitted, say one who has been observed by an atom deep inside this gas cloud. Now it is being repeatedly absorbed by another atom again in this gas. So after being repeatedly absorbed, they will finally escape it. It might take some time. Now these re-emitting photons escape from this gas cloud and they travel around different directions. It can go in all possible directions, not just this one where we are observing the light, right? Note that these re-emitting photons are at the same frequency as absorption lines as well as different lower frequencies. Okay. Due to the scattering in different directions, what happens is that the intensity here, the intensity of the light corresponding to these frequencies become very low, and as a result we effectively observe the absorption line only. Okay, so this is the reason why even if there is a bright line spectrum in different direction, in this direction we still observe continuous spectrum with dark absorption lines. Okay, so now you see the same old thing I have shown here. So this is our case 3. So bright source of light which is emitting photons being absorbed by a cloud of gas. So we observe continuous spectrum with dark lines, and this is again the intensity versus wavelength plot which I have just drawn some time back. Okay, but in a different direction we will observe bright line spectrum, okay, like this. And of course this continuous spectrum when seen through a spectroscope will have light from all frequencies. Okay, so after this basic discussion about what to expect in stars, in outside space, what type of stellar spectra we can expect, now let us proceed to the most simplest possible spectrum out there. And what is it? It is the solar spectrum. Okay, now on your screen here what you can see is very interesting, various possible spectra from various possible sources. Okay, now here you can see not only daylight but also the spectra from fluorescent bulb as well as a cool white LED, right, and an incandescent bulb as well. Now interestingly, what I wanted to tell you is that all have very different spectral response. They are not the same, they are very different. Now this is what we are interested in, daylight or the solar spectrum. So how does it look like? Well, this is how it actually looks like, this stellar spectrum. Now this is just a basic idea over there, but this is the real one, real stuff, how it looks like this. Okay, so this is how it looks like, the stellar spectrum. Now what do you think you are observing? You tell me. Yes, so tell me.
Sir, lambda versus the intensity কমছে.
Okay, lambda versus intensity কমছে. আর কি দেখতে পাচ্ছ? What more? There are so many absorption lines. Can you not see them? Okay, I will come to it in just a minute. Now, what more is there? Okay, so what is this? Again, the same solar spectrum, but this time we are seeing this part which corresponds to the visible spectrum. So you see, this is the only part which corresponds to the visible spectrum, and here I have shown it in a much enlarged form over here. Okay, visible part, and this corresponds to ultraviolet part, and these are infrared parts of the spectrum. Okay, next. Okay, here. So basically, if this is the intensity, then you see we have got ultraviolet part as well over here. And how much is this? It is approximately 3.5%. And here we have the visible part, which corresponds to say 42 to 43%, right, of the intensity. Then what about the near infrared to far infrared? They correspond to around 52 to 55% over here. And less than 1% correspond, but it is still there, corresponds to microwave to even radio wave range, right? So this is more or less a rough idea of what is going on in the solar spectrum. Now let me try to see if it is possible. You remember I was saying that what are these? These are basically absorption lines. As I was just telling you before, there will be some absorption lines and we will talk about it in more details. Now this is just a representative spectrum, so we want to see this again, whole plot, in a plot like this. Is it possible? And yes, The answer is yes. So this is the entire spectrum of the sun. Over here you can see, starting from violet to red, 400 nanometer visible part only. Here to here, visible part only. 400 to 700 nanometers is there. And this is the detailed solar spectrum. So violet to red, the entire length has been shown here in this horizontal both. So the horizontal graph has been shown in a horizontal plus vertical pattern together. But the most important thing is you can see so many dark absorption lines. So this means that there is a lot of information contained in this solar spectrum. Okay, now let us try to analyze this solar spectrum. So this is what we will try to do now. So let us start analyzing the solar spectrum. Now we just observe that the entire solar spectrum, what does it looks like? Well, it looks like something like this. It is just approximate. There is something like this, kings over there as well. Now, okay, so this is the spectrum. Okay, this is wavelength, this is intensity, arbitrary units. Now tell me, as I was asking you before, what do you observe in this and where have you seen such things? The first thing to observe is that you see there is some sort of a nature like this. Do you observe some sort of average nature? This is the first thing to observe. And next is these absorption lines, these ones, what are they? Now, so one is a broad distribution and next is absorption lines. Okay, now where have you seen such broad distribution and what do you expect? Anybody? Such sort of broad distribution, come on.
Radiation curve.
Yes, very good. Black body radiation curve we have observed, and it will be interesting, that that black body radiation curve can have different natures. This one as well. This is not correct. Yeah, we can have black body radiation corresponding to different temperature. So this will be a say 2000 degree Kelvin curve, and this curve where it broadly follows this nature, it approximately corresponds to 5800 Kelvin. So this is important. So this broad distribution, this approximately corresponds to black body radiation. Okay, now what does this tell us about black body radiation? Why black body all of a sudden? Now what is black body? Well, we do know that basically black body is the thermal electromagnetic radiation within or surrounding a body in thermodynamic equilibrium with its environment. Right? And it is emitted by a black body. Now, this thermal radiation spontaneously emitted by many ordinary objects, it can be approximated by black body radiation. So what about a perfect black body? Actually, it does not exist, a perfect black body. A very close one will be a perfectly insulated enclosure that is in thermal equilibrium internally it will contain blackbody radiation and will emit it through a hole made in its wall, and there is a condition, which is that the hole has to be small enough to have a very negligible effect upon the equilibrium. Now remember, when I am saying blackbody, I just gave you the definition, and blackbody means the body is in thermal equilibrium with its environment. So what about stars and planets? So this is the spectrum of a sun. So does this mean, is the sun really in thermal equilibrium with its surrounding? Of course not. It is not at all. Not even the planets. Both the planets and stars, they are not in thermal equilibrium with their surroundings. And also they are not perfect black bodies. Why? If they have been the perfect black bodies, then there will be no absorption line also. And also, if you observe closely, there is a broad distribution, but it doesn't exactly correspond to the spectrum of the sun. There is a difference, and I will talk to you about this difference now as well. So, but remember that, in fact, there is one heavenly object which can be considered as near perfect black body. And what is that? You know it.
Black hole.
Yes, black hole. They are the near perfect black bodies, and in the sense that they absorb all the radiation, that's why they are black, that fall upon them. And it has been proposed, in fact, that they emit black body radiation as well, which is known as Hawking radiation. Yes, I will talk about it when I discuss black body. They are very interesting stuff, and we have also black body thermodynamics as well, a very interesting topic. So, black bodies, they have been proposed to emit Hawking radiation with a temperature that depends entirely on the mass of the black body. Okay. So, any questions till now? Bolo.
স্যার বলছি তাহলে আমরা হকিং রেডিয়েশনটাকে স্যার বিশ্লেষণ করে ব্ল্যাক বডি সম্পর্কে জানতে পারবো অনেক ডিটেইলস?
Now there are many speculations about it, but experimentally right now, you know, it is difficult, right? Okay, so we found some features from the solar spectrum. Now the next question to ask is the sun really a black body? So, can we really consider the sun to be a black body? Now I have already given you some answers that there are spectral lines present, so it is not. But let me now talk about overall scenario. You see, since the sun has no solid surface, so any radiation that hits the sun, if this is the sun, so any radiation that enters the sun, of course this is not a solid surface, remember, and definitely this picture can never be scaled. Okay, now since the sun has no solid surface, so any radiation that hits the sun, what will happen? It will eventually be scattered, and afterwards it will be absorbed inside it until it is completely lost, various scatterings and absorbed finally. So what does this make? This makes the sun very close to being a black body, as far as absorption is concerned. Okay, but what about emission? You see, it is not a perfect black body radiator, and there are reasons as well. You see, at its apparent surface, the sun is never a perfect radiator, because I gave you the reason, right? Because of the presence of absorption of the electromagnetic radiation at individual wavelengths by various atoms. and ions that block part of the outward flow of the radiation. Now why does this happen? This happens because the interior of the sun over here, it is much more dense and hot, but the outer region, this outermost region is known as chromosphere. This is the outermost region, and this has very less density. Okay, and not only that, it is cool enough for electrons to be bound to nuclei over there. So you can find atoms, but you will not find atoms over there. There will only nuclei and electrons separate will be there. But here we will have atoms. And what will happen? You see, so atoms in this cooler temperature or cooler atmosphere, chromosphere over here, compared to the hotter interior, they can get excited. And after they get excited, what will happen? They will absorb photons of certain energy. So photons which are being emitted from there, they will absorb the photons corresponding to their energy levels. And these transitions, because of them, we will observe on Earth. What do we observe? We observe the dark absorption lines. Okay, we observe the dark absorption lines. Now this blocked radiation causes excitation and ionization of gas, causing it to emit extra electromagnetic radiation at unabsorbed wavelengths. Can you give me a reason why this is happening? Let me give you an example. A very nice example. I've just given you some idea previously. So you see, if this is one of the energy levels, okay, so this is ground state first, just numbering, and suppose there is some absorption over here, over which fourth level this atom gets excited, having energy E0. So this is the fourth level. Now what will happen during the de-excitation? You see, during de-excitation, as I was saying, we can have this part, this branch, all of them, they are possible. Even this branch is possible. So only one absorption can cause 1, 2, 3, 4. So we can have, say, E0 prime, E0 double prime, E0 triple prime, and E0 4 primes. Right. Of course, this E0 is greater than each of them. This is basically sum of this one and this one, or this one and this one. It is sum of them. Okay, and this is the reason we will observe extra. So even if this is absorbed, so many ones are getting excited. You see, if one atom, we get this de-excitation, and also this one is possible as well. So we can have this de-excitation gamma ray as well, or photon as well, along with 1, 2, 3 and 4. So how many are there? So one excitation here is causing 1, 2, 3, 4, 5 de-excitations. So this is what I am saying, that the blocked radiation causes excitation and ionization of gas, causing it to emit extra electromagnetic radiation at unabsorbed wavelengths. Thus, as a result of this line absorptions, we get extra radiation. Okay, extra radiation. Now let me show you. You see, if this is the solar spectrum, now if I closely look into this is how it was, then okay, then the one that corresponds to the black body actually has a nature like this. So here you see these are some extra part. Here they are above the black body profile and they correspond to these extra lines. Okay, so and this profile actually corresponds to 5780. This is the real number, Kelvin. So solar surface corresponds to the black body with 5780 degree Kelvin temperature, black body. Okay, and this is our solar spectrum, this one. Fine. So what did we really gain? So from this graph we observe and infer that the outer surface of our star's spectrum, so sun, is quite similar to a black body spectrum at a certain temperature. That one is 5780 Kelvin. Thus a stellar spectrum can be approximated by a black body spectrum. So this is the thing that I wanted to talk about. So this is the reason, one of the reasons for analyzing solar spectrum. So we were analyzing solar spectrum, right? And after analysis, what did we observe? We observed that we can approximate the solar spectrum, approximate as a black body, okay, spectrum. What more? So instead of directly going to the surface of the sun and measuring using a thermometer, of course that is rubbish, not at all feasible, possible, even foolish to think about. What we are going to do, since we have established this, there comes the physics into play. Since we have established that this can be approximated as a black body spectrum, so we are going to use the laws of black body radiation for estimating the temperature. Now this will be the effective surface temperature of the sun. Now how many laws are there? The first one, you remember, it is the Stefan-Boltzmann law. Right, and as a result, what do we have? We have F is equal to sigma T to the power 4, and from here we can get information about effective temperature, this T effective. The second one is Wien's law. Okay, and so here also lambda max in the distribution, this one, lambda max into T is equal to 0.28975. This one. Here also we can get information, but compared to these two, this is a better one, because this does a overall. Here you can have an overall plotting as well. You try to fit the overall plot, but this one only does at one single point, the maximum. Okay. Now before I conclude today's lecture, there is one last thing I would like to talk about, and it is that, you see, just a second, here. So we are talking about sun. Now the very outermost layer is the chromosphere. And the layer just below it is actually the photosphere. I will talk about it more details when I talk about the stellar structure, radiative transport section, and there I will little bit touch the stellar atmosphere sections as well. Now this photosphere of a star is actually the region where the emitted light is generated, okay, and it is idealized as a layer within which the photons of light interact with the material in the photosphere and achieve a common temperature, okay, which is maintained over a long period of time. Now note that some photons can escape and are emitted into space, but the energy they carry away is replaced by energy from the interior part of the star, so that the temperature of the photosphere, it remains constant more or less. Now changes in the core, inside the core over here, you see the changes, they can lead to changes in the supply of energy in the photosphere over here. But such changes are very slow on the time scale of interest for us humans. Our time scale is very small. Now assuming these circumstances can be indeed realized, you see the outer layer of the star is somewhat analogous to the example, this one, analogous to this example that I was mentioning before, of an enclosure with a small hole in it. This one, small hole in it, the enclosure, with the hole replaced by the limited transmission into space. This one, yeah, there can be limited transmission, and this is the similar transmission of the photon into space at the outside of the photosphere. Now with all these assumptions in place, you can say indeed that the star emits blackbody radiation at the temperature of the photosphere, and using this model the effective temperature of the star is estimated. Okay, so you must remember this stuff, that the energy is being constantly being replenishing, the energy carried away by the photons outside, okay, and thus we define this as the temperature of a black body that yields the same surface flux of energy as the star. So any questions? So this effective temperature, what is this? It is basically the temperature of the black body. So this is our black body, the sun, that yields the same surface flux of energy as that of the star. So basically you can say that we are replacing the actual sun by a black body, and then we do our measurements on this black body. But remember, this is not the real sun, because the real sun has many other artifacts as well, but it is still better than having at least nothing. Okay, so questions? Hello? Yes, dark absorption lines. So were you guys, did you get some idea about the stellar spectrum and also solar spectrum and how we can extract information about them? I think this is quite fun, trying to understand like this way. Yes, but not operating right now. Yes, various other important aspects. You see, for the other stars, they are very far away. Even using the Hubble Space Telescope and even more advanced versions as well, we are still unable to get all the minute informations which can tell us about the details of what happens inside the star. So we are right now trying to get information, extract information from the sun. You see, in the plasma astrophysics, there are many unexplored questions also regarding the solar core, how the corona behaves. There are many things. So if we go close enough to the sun and get observations, we can get observational constraints again, and then those theories can be fully developed regarding the solar corona, solar cycle. Then what will happen? You see, we can predict how the sun will behave, and we will take precautions, knowing someday that something very drastic will happen. Suppose all of a sudden the sun emits huge number of neutrinos or some very large number of charged particles, high energy photons as well, then we will just die. But suppose we know prior to that something like that is going to happen, at least we will be able to do some preparations. So this is what we are trying to do. Come on, sun is essential for our life. Had there been no sun, we will just freeze to death. Even with the latest technology we'll have, not a human will be alive even after 1 month if the sun dies out, even if you go underground as well. Okay.
স্যার বলছি যে স্যার এই সেকেন্ড যে লেকচারটা নেবেন স্যার সেটার কি
স্যার বলছি স্যার আমাদের সানের যে এফেক্টিভ টেম্পারেচারটা বার করছি ওটা তো ব্ল্যাক বডি ধরে ওটাকে
ইয়েস,
তাহলে স্যার ওটাকে আসলে তো সানটা তো ব্ল্যাক বডি না, তাহলে কি এক্সাক্ট টেম্পারেচার আমরা পাই?
আমরা দেখো কি করতে পারি, আমরা ডিফারেন্ট টেস্ট করে দেখতে পারি, ডিফারেন্ট অবজারভেশনস করে দেখতে পারি, অ্যান্ড দেন উই উইল ট্রাই টু ম্যাচ with that of black body. কোথাও কোথাও অনেক জায়গায় deviations দেখা যায়, then we develop theories to explain those deviations. But at least you see, you remember the Taylor series? The first term of Taylor series is very important. After that we can have certain approximations, so on and so forth, but it is important to have the first term as well. So this is our first getaway, first basic approximation, and then we will talk about how to deal with non-black body type radiations, how to do those approximations. I will talk about it somewhat. You will see, you will get actually, if we write down the solar flux, we have a sort of series expansion. The leading one can be described using black body or so, but there are other non-black body parts as well. I will discuss it in very details when I discuss the radiative transport part. Okay?
ওকে স্যার,
ঠিক আছে।